All right, Calculus 30, Section 7.2. We're talking about derivatives of sine and cosine. And I've got a sine graph here. And actually, before I get too far, I want to show you something really super cool here, which is over here. Graphs of sine, cosine, and tangent. On Math is Fun page, check out the sine wave animation there. For some reason, that is just completely satisfying to me. I just think that is so awesome. That could just put me to sleep. It's just perfect. But you can sort of see how when the sign changes, and actually if I hover my mouse over it, I can kind of totally manipulate it here. Right? But the sign over here at 0 is 0. As the angle increases, so does the value, right? And the graph. So it just kind of maps it as you go around in the circle as fast as you want. So anyway, so this is awesome. I'm just making, this big long wave. Okay, and then I'm unraveling it as well. So this is pretty cool too. So anyway, so I would encourage you to go to Math is Fun, because it is, and this is a great site. All right. So on that note, let's talk about derivatives of sine and cos. Okay. So I want you to quickly sketch a sine graph. It doesn't have to be perfect, but do one period. So that's 0 here to 2 pi. This is your typical sine graph, what it looks like. And I want you to draw a graph underneath that kind of looks like this right here. So just a mirror of this graph. So 0, we're going to do pi over 2 here. We're going to do pi, and so on. 3 pi over 2, and so on. 2 pi. Okay. And what we're going to do is we're going to map the derivative of sine onto our graph here. Now, I guess one thing we will need to do that I don't have on here right now is to put, I'm going to extend it, I have to extend this graph down a little bit. I'm not sure why that's not there. Actually, I kind of forgot with that. So, this is what we're going to do. This is how we're going to do it. So, on the original graph here, sine, I want to first outline where the derivatives are equal to, what is this derivative equal to? A horizontal line there? Equal to 0. Okay. So can you see that at pi over 2, the derivative is 0. So again, this is y equals sine x here, this graph. This is going to be sine x, the derivative, right? Or written another way, d over dx of sine x. Okay? So this is 1 point. All right, where else is it 0? Is it 0 here? Is that 0 there? No, that's not 0 there. It's 0 down here, right? Okay, so at 3 pi over 2, it's 0 again. So you see, what I'm doing is I'm plotting the value of the slope of the tangent line. That's the value of the derivative. Okay. So right about here, it's tough to tell, but right about here, let me see if I can draw a line here for you. I don't know if this is going to work very well, but anyway, so this would be like a tangent line here-ish. I'm going to have to move this. And that's going to work just terribly. So something like that. Now, if we could actually, take our measurements here. What this is it's a slope of 1. Okay? It's actually a slope of 1. So what we're going to do right here, at positive 1, we're going to make a point. All right? So where else would it be positive 1? Well, it would be positive 1 right here at 2 pi. Okay, so we're piecing this together. Now, over here, right, and again, I'm going to do my best here. Over here, we've got a slope of, if that's positive 1, guess what this is? Negative 1. All right, so we're going to go negative 1 down here. And if we put in a whole bunch of tan lines here, tan lines, do you have tan lines? Hey, it's winter, no tan lines. So what you would find is you would have something like this. Okay. And what does this remind you of but the cosine graph? Okay. So if you plot all the values of the tangents on a graph like this, we have this. The derivative of sine. Now, is this exactly cosine? Does it look exactly like cosine? Yeah, it is. It is. Yeah. It is. I mean, these dots, you have to trust me with these dots. But yeah. It's exactly cosine, okay? So that is that's the first big deal here in this lesson. The derivative of sine is cos. The derivative of sine is cos. So what do you think the derivative of cos is going to be? You think it's going to be sine? All right, let's find out if it's going to be sine. What? Cosecant. Oh. Any other guesses here before we begin? Okay. So here we go. It's pi over 2, and it's 90 up there. Okay, you got degrees on this one. Big deal. Okay, 2 pi. All right, so you can probably see what's going on here. Let's quickly do this because I don't want to, you guys are already working ahead of me here. So we've got a 0 slope there. 0. We've got a 0 slope here. 0. And we've got a 0 slope over there. 0. Okay. This is -1. -1 right here. Right here. Drop that down. -1. And here is it is a positive 1. Yep. It's a positive 1. So let's put a point there. Yeah, something's wrong there. You're right. Wait a minute. Wait just one doggone minute here. This actually is not y equals cos of x, right? Yeah, good job. This should be just pi. So this is this red graph. Very good. You notice that? Now, I don't know if you noticed what you noticed, but you're right. This doesn't look right because this should be for cos. Where is my pen now? I just used black. It should be pi. This actually is. Does anyone know what graph this is? Because one period length for cos should be 0 to 2 pi, right? So this is only 0 to 1 pi. So what is that? This is what is this? 1 over 2 pi cos 2x. Remember? Anybody remember that? I think this is cos 2x because it's squished in. There's two complete periods within 0 to 2 pi. So thank you. I got this off the internet. The internet is evil, okay? Just so you know. This is not correct. It's not just in degrees. This should be 2 pi. This should be pi. This is pi over 2 right here. Okay. Note to self. Don't trust the internet. Be more careful.
So the derivative of sine x is cosine?
Yeah. That's everything's fine up there. I think this is that's correct. See, I got them from the same. I thought from the same site, but anyways, apparently not. I didn't even look at the axis there. Okay, so this is cos. Everyone agrees this is cos. Sorry, let's back up. Now, what we're going to do is we're going to fill in the blanks here, right? Okay, so this is, these are some more derivatives, or some more tangent lines. And so it kind of looks like this. This is sort of what it looks like. Now, what does this shape of graph remind you of? Sorry? Okay, it looks like a sine, but it's a sine that's been flipped upside down. So, the derivative of cos x is actually negative sine x. And that's the second big deal here when we're talking about derivatives of cos functions. Okay, now that we got the axes figured out there. Okay, so any questions there? Now again, this is a function, right? So if I give you, let's say we got a sine graph, okay, and I actually want to find the. Let me just sketch this out here. I'm not going to take one off the internet. I'm going to sketch this out myself. Okay. All right. Whoa. So let's say I have a sine graph that looks something like this. Okay. And I want to know what the exact slope is of the tangent line at, now let's say, so this is pi, right? This is 2 pi. This is pi over 2. So let's say I want to find out at this value right here, what's it going to be? 3 pi over 4. I don't want to use 3 pi over 4. Let's use, what's the value between 3 pi over 4 and pi? Let's do 7 pi over 8. How about that? So 7 pi over 8, that's going to be right around here. I want to know what the value of this slope of this tangent line is. Exactly. Okay? So what I'm looking for is I'm looking for the derivative of sine evaluated at what? 7 pi over 8. So we're going to find the derivative of sine x, and we're going to plug 7 pi over 8 into the derivative to find the exact slope line. So let's just see if this works. So what we've said is the derivative of sine x is what? Cos x. So if I want to evaluate this, and actually the notation really should be more like this here, then you want to put it at 7 pi over 8. Something like that. So cos x at 7 pi over 8, we're going to look for cos of 7 pi over 8. And this exact value should be the slope of this tangent. So we kind of have a rough gauge here. That's really bad. We have a rough sort of, it should be negative something, I guess, right? And it's pretty close to pi, so it should be a fairly large negative number. So what's this going to be? Let's figure it out. If you're using your calculator, make sure it is on radians. And do cos 7 pi over 8. Negative 0.923. Okay. Well, I guess this right here would be negative 1. It doesn't look like it on my graph, but that's negative 1. So this one's going to be pretty close to negative 1. Or negative 0.923879. Does that seem reasonable? I think so. All right, so it makes sense. Okay, any questions? So if we're going to test this out in decimals here, let's do sine of x. Okay. All right, sine of x. Okay. So 7 pi over 8, what's that in the decimal form there? Somebody find that out for me, just hang on with it. So I'm going to also put y equals negative, what was our value there? Negative 0.923879. Negative, 0.923789, was it? X. Okay, 923789795. So what we're going to do here is I want to see if this slope is reasonable. So what's the decimal form of what's the decimal value for 7 pi over 8? What is it? 2.7488. Okay, 2.7488. So right here. So at this point, I don't know if I can actually put a dot there. But at that point, okay, I want to see if this slope looks like it could be a tangent there. Do you think it could be? Whoops. Let's do plus b. And yes, we're going to do a slider for b. So check this out. I'm going to move this over and see if this is a tangent line at about... They touching? Not really. They're touching over here. Let's say 2.9. What did you say? I don't think. Yeah, I think we have to back up there. 8. Nope. 2.97. Oh. 9.3. I can change the step here, but Anyways, so you see what I'm getting at, right? We're trying to find this tangent line right here. There's probably a way I can do it in Desmo, so I just don't know how to do it. I'm just messing with the intercept, right? So where do we have to come back to? Do we have to come? Let's zoom in. Oh, let's see. Let's see. Oh, we're quite a ways away there, aren't we? So we got to bring that down. How about 1? Oh, what was the 2? That's dangerously close. Oh, 2 5's too much. 2 3, come on. Okay, so let's say this is pretty close. Okay, so I guess the bottom line is this slope. Okay, we zoom back out. Does this slope look like it could be the slope of the tangent line at that point there? Yeah. Okay, and there probably is a way in here to actually do that, but this is what we're testing. Okay. So now we can use all the different rules that we've learned already. Like, for example, if we have y equals sine of 3x, what is the derivative of this function? So now that we know what the derivative of sine is, we can use it in conjunction with all the other rules. So, for example, what differentiation rule are we going to use here when we have to find the derivative here? What's the one that jumps out at you here? What are we going to have to use? Product rule? Sum rule? Something else? What's it? Chain! Nice. Yeah, you use chain rule. Outside function, inside function. Okay, so what's the derivative of sine of blah? It's cos of blah. And what do we do if we have an inside function multiplied by the derivative of the inside function? So y prime is 3 cos 3x. See that? That's an S. Okay. Another one, y equals cos of 2x minus 1 all squared. That's terrible. That's going to be a tough one. So how do I do that? Well, y prime is going to be, now if the squared is here, is the squared on the whole thing like this? Is that what it means? Or does it mean something else? Tell me. Just on the bracketed stuff. Yes. If I wanted to show that this was all squared, I could either put brackets like that, or where would I put this to? Right on. I would put it right there if I meant I wanted the whole thing squared. But I don't. Okay. Very good. So what that means is we've got an outside function of the cos. We've got an inside function of 2x minus 1 all squared. And we have a yet inner function here. That's what that means. So the derivative of cos of something is what? Thank you. Negative sine of, I don't touch anything inside there. Nothing. Instead, I multiply by the derivative of the second layer. That's going to be what? 2 times 2x minus 1 to the power of 1. And finally, times the derivative of the innermost layer, and that's going to be times what? 2. Okay, so when it's all said and done, y prime here is negative 4 sine of 2x minus 1 squared times 2x minus 1. Does that look right? No, it's not 2x minus 1 cubed. Thank you for asking. Thank you for asking. This 2x minus 1 squared is a part of this sine function. So it's not a separate function that we can go ahead and multiply by this. So no, they have to be separate, because this squared is attached to the sine function. And this is something totally different. Great question. I'm glad you asked that, though. All right? So anything that's inside a sine or cos or tan or arc sine or whatever it is cannot be combined with anything that's not.
So can I write minus 4, 2x minus
Yep.
1
Yep.
sine?
Sure. Yeah, you can write this wherever you want. You can write it over here if you want. Yeah. Doesn't matter. Okay. Excuse me. Any other questions at this point? Okay, so here's a little shot of the textbook. If you're at home and lonely without your textbook, you need to see some of these. I know you get lonely. So what?
I didn't realize we posted it at the start of the day. It's not cool.
Yeah. Yeah, that's right. I probably posted it on Google Classroom for you guys. Yeah. That's true. Sometimes even that's too much to look up, I guess. So I'll just throw it on the video here. Ooh, problem plus. These are fun. You should do the problem plus too sometime. I think there's almost always a problem plus at the end of the section.